All right, let's go ahead and kick this off. Thank you very much, everyone, for joining. We appreciate you being here today for the second session in our 2021 PTP Masterclass series. Today's topic is Unifying Timing for Modern Broadcast Systems. My name is Gina Angelia. I'm part of the marketing team at Imagine Communications, and I'm pleased to be your moderator for today's session. Just a little bit of housekeeping first. We'd like to remind you that this session is being recorded, and you can look for the playback coming up, along with the recording from last week session if you missed that one, and session 3 coming up this same time next week. We hope you'll be able to join us for that one as well. Your keynote speaker today is Lee Whitcomb, SMPTE Fellow and Solutions Architect here at Imagine Communication, and he's joined by our esteemed colleagues, Robert Welch from Arista, he's Principal Networking Engineer there, and Mike Wadeson, also SMPTE Fellow and Application Engineer from Telstream. We here at Imagine Communications are proud to partner with both Telstream and Arista and participating in all the interops and JT testings that have gone on. And we'd like to thank both of them for their continued support and leadership. And of course, thank you to everyone on the call for joining today. We'd like to remind you that this is going to be an interactive session where possible for you. And we invite you to enter any questions you may have using the Q&A button you're going to find at the bottom of your Zoom webinar. We actually have a team of experts in the background from all 3 companies, and they've taken their time today to join us and help answer your question. And we appreciate them being here. So we encourage you to use that Q&A button at any time during the broadcast to reach our experts. So once again, we are recording today's session and the playback will be made available in the next few weeks. So with that, I will pass the broadcast over to Lee Whitcomb and our panel of PTP experts. Lee, the show is yours.
Thanks, Gina. So just a kind of a review of where we're at. So last year we did a 3-part webinar series. So we did some introduction to PTP. We then looked at some PTP architectures, some various best practices, then went into sort of commissioning and troubleshooting. Then in the fall, we had a PTP Best Practices webinar focusing on that. And then last week, we started our second webinar series here, and we covered the integrity and monitoring. And today we're going to be getting into unified timing of a modern broadcast system. So just a quick little review here. So in the PTP best practices, we had a bunch of best practices that are focused around sort of the network architecture and topology. Then we came up with a bunch of best practices that are related to the PTP network architecture. So differentiating the PTP network from the sort of more general networking stuff. We then had a bunch of best practices that are related to the PTP configuration. And then lastly, some that are related to commissioning and operations, because I mean PTP is a very critical flow in your system. So what are we going to cover today? Give you a quick update on where the standards are at and what's sort of been happening there. We'll go through a variety of use cases, which we'll sort of spend most of our time there. We'll take a look at 2059 and PTP monitoring, and then lastly we'll go over a bit on how to secure your 2059 PTP systems. So on the standards, so SMPTE has updated all the core sort of PTP standards, so there's the 2110 standards. So the -1 standard, which was published this year, 2021 here, the IEEE Explorer backend is where we host the SMPTE standards. So that document is available at the link I've shown there. Just note that all the sort of the core 2110 standards, as well as the PTP standards from SMPTE, are all currently available for free. So where maybe not every standard is available for free, all the 2110 and definitely the PTP ones are available. So in the SMPTE update here, we sort of clarified some equations and stuff. We didn't actually change anything. We just made it a bit clearer. Then we have the -2 standard, which again was also updated this year. It's available at that link there. Again, we were sort of doing some clarifications for the most part. The one change we did do is that the default rate for the announced interval we changed. Now, at a lot of our best practices and other previous webinars, we've already been giving you a heads up that we were changing the announced interval default, the recommended value, from -2 or 4 messages a second to 0 or 1 message per second. So now this is sort of beneficial. We also sort of clarified some stuff in the communication model. Again, we didn't change anything. We just improved the language because some things weren't quite as clear as you could. Just one little note there, because we've seen this a few times in the field, is in the communication model there, when it comes to PTP management messages, if a device is responding, it shall respond with a unicast message. And so that hasn't changed, but just want to reemphasize that, because we have seen cases where if people are using unpatched PTP4L implementations, they basically are non-compliant to the standard. So just be careful that if you're using a device that's using sort of the PTP4L implementation, it won't actually be standards compliant. IEEE is also working, or has done an update. Their version, they say 2019, although it was actually published in 2020. Just kind of a key note there is it is sort of backwards compatible to the V2 for the most part. They've done some stuff like the hybrid communication model they've clarified, which sort of makes it consistent then with the SMPTE model there. They've added some stuff on security, monitoring, some other changes. Also, we've been working on some terminology updates. So we've been trying to remove sort of culturally sort of insensitive or offensive terms. SMPTE has gone through and updated most of our documents. We have just a couple EGs left to finish. For IEEE, it's sort of work in progress. So they still have a sort of a ways to go. They have gone through a process of evaluating different terms. Fortunately, they've sort of picked the same terms that SMPTE has used. So this is the word which was master is now going to be, is being replaced with the word leader. So if you have like master clock, it now becomes leader clock. The term slave has been replaced with the word follower. So if you had slave clock, it now becomes follower clock. Just note that the noun grandmaster remains. So grandmaster remains. Those are sort of changes that you'll see in the SMPTE documents, in our newer webinars, and in the newer standards. Okay, getting on to the use cases here. So we're going to cover seven use cases today. And for each of these use cases, we'll sort of outline, kind of define what the use case is, so that's clear. We'll go over what some of the challenges are with that use case. We'll look at different sort of solution options, some pros and cons of the different options you may have, and then kind of just summarize some of the key takeaways for each of the different use cases. So starting with kind of our simple, I'll call it the baseline one here. So you want to put PTP over a 2022-7 network. So 2022-7, which is part of our 2110 suite here, what we're doing for our Essence, our video and audio flows, is we're transmitting the same packet on multiple links, and then a receiver will receive all these links, and as long as that packet exists on one of those links, then the receiver can receive the stream. One of the challenges that comes when we're putting PTP over these networks is that that redundancy model and the PTP redundancy model using BMCA are very different. And so we just have to be careful that they work together. And with all our use cases we'll cover, an important thing is we want to make sure that in the event of a failure, a switch failure, a link failure, device failure, that the entire network and all the devices are still getting the time from the same source of time. So that's going to be a common theme we'll see in all the use cases. So looking at kind of the key components of this kind of a solution here. So we want to make sure to use boundary clock switches connected to the media node. So the switches at the called the lowest level connected to our media node. Just make sure that my cursor is coming through okay. Someone should confirm that.
Looks good. You got it. You're pointing.
Okay, good. So we want to make sure that these lowest level switches are in boundary clock mode. Now, the one key thing too is we want to make sure that the entire network converges to one source of time, one grandmaster. So in the event of any link failure, any switch failure, everything converges to one spot. So the one thing which is a little different, you may think of, oh, in 2022-7, I want to have this air-gapped system. So I want the two sides to be completely separate. Now, from a PTP point of view, we don't want that. We actually want connections between the two sides, and actually we want at least two connections so that if we have a link failure or we have a switch failure, the network all converges, both the blue side as well as the sort of red amber side all converge to the same source of time. Want to make sure to have a consistent PTP domain across the entire network. So both sides of the -7 here, say in this example here, are both set to domain 42. And then from a -7 point of view, we are connecting to both the blue switch and the amber switch. Now, one thing just to be careful, because there's been some devices been a little bit confusing on sort of what a boundary clock is. So just to be clear, so a boundary clock switch, all the interfaces have boundary clock processing. So they have special logic to do boundary clock switch processing. Now you want to be careful because there are some switches which may have kind of boundary clock on a couple input ports, but then the core fabric is actually non-PTP. So these ports down here are just rounded fabric. And just note that that is not a boundary clock switch, because for a boundary clock switch, all the interfaces must follow the boundary clock rules. And why is this important? It also sort of comes into why is a boundary clock a very powerful and useful device? So with the PTP processing, even though PTP is multicast, it in theory should go to every device in the system. With boundary clock, it kind of terminates the signal. So you kind of have this private link here. So this basically prevents traffic from one device impacting the other device. And this can become quite important. Like in a large system, maybe you have like hundreds of nodes. When we saw one customer where they had, unfortunately, this kind of configuration, and they were basically seeing, because every PTP device was seeing all the messages from every other device, these poor media nodes were getting like 10,000 messages per second, where, I mean, really with a proper boundary clock, you should be getting like 25 messages a second. And so these media nodes were getting pounded with like 10,000 messages per second, which puts an awful lot of load on them. So that's one sort of the power of the boundary clock. So that's why you don't want this. See later on in the security section, it sort of bypasses a lot of the security features, and it makes it much harder to debug. So we want to make sure to avoid any time where we have these non-true boundary clock switches. So at that lowest level, we always want to have those. Okay, so just a quick review there. So we don't want that full air gap. We do want those connections. We want to use those real boundary clocks, avoid these non-PTP, and we want to be using all the best practices in our previous presentations. Okay. So that sort of first use case that we just saw there, that will cover us. So imagine you have like a single switch, take 30 ports, is very common. So 3100 gig ports going to a media device that say it does 32 channels per device. This gives you around, say, 900 3G channels in that sort of simple system. So, I mean, that sort of emulates like a 512 squared router, gives you maybe like 14,000 audio pairs. Now, some systems are bigger. So what do you have to do for that? So some of the challenges when we're scaling things up, we need to sort of think about, because you may have a large facility with multiple locations, so security, the management between the different locations. Also where we put our grandmasters, we have to sort of maybe think through that a little bit more. So lots of different options, different pros and cons. So one option here is that, so we have our sort of our baseline system at the bottom here. And then we're going to have to add sort of extra layers of switches above that. So one option, kind of our preferred option here, is that we use boundary clocks at the top level. So boundary clocks at the lowest level is very critical. As we move up to the higher levels, there is less traffic. There's not as much scale issue. So you don't have to use boundary clocks, but they're still very useful. So that's sort of one option to consider. You could use transparent clocks. So one question you always want to ask yourself is, what problem are you trying to solve? And sort of keep that in mind. So, like, say, for instance, I'm very paranoid. I don't trust the boundary clocks, and I want to be able to Wireshark the traffic from the grandmaster. So to do that, I might say want a transparent clock. But you sort of always have to ask yourself, like, sort of, what problem am I trying to solve? And then make sure that solution, whether I'm using transparent clocks, boundary clocks, and so on, is covering that. At the highest level, I might be going between multiple locations. So I may want to sort of be a little bit more cautious on my sort of security and access control there. So I may want to consider using unicast versus the multicast. Another sort of consideration is where do I want to put my grandmasters? Typically, you sort of say put them at the top logically, but one thing to keep in mind is that these higher level switches, I mean, often they're running with 400 gig or 100 gig ports, and the interfaces from your sort of grandmasters are often sort of 1 gig or 10 gig. So you may not want to consume, I'll call it a more expensive 400 gig port on one of these switches here. And you may want to sort of move your grandmasters down a little bit in the architecture here, noting that sort of with the BMCA and everything will converge. The convergence time might be a little bit more. So you want to sort of, again, sort of keep that in mind. So some different sort of options to think about. Robert and Mike, you want to sort of maybe add a little bit to this?
Yeah, this is really good. In fact, one of the questions that just came in, I was just going to respond to Kevin is, does transparent PTP basically mean that it's not a PTP aware switch? And that's pretty much what it is. We're just doing multicast on that. And as you said, Lee, very well, and let me turn my video on here, apologize for that, is you want to make sure you're doing IGMP snooping query, so you're not flooding, number one. Number two is, as you mentioned, if you want to Wireshark the pure PTP messages, if you were in boundary clock mode, you wouldn't be able to do that, but you would be able to do that if you were in just a standard multicast, kind of a flat switch. Now, the other things to consider is, people might put in the transparent PTP layer there, just a quote dumb switch from, well, what we used to call fries here in the States, but that's gone, but just any off the shelf switch. And you don't want to do that because you want to have predictable packet pacing. You want to have something that's scalability multicast wise. And this is very important because if you don't have something at that beginning layer, then you kind of have that residual effect all the way down. Mike, thoughts on that?
Yeah, maybe just to clarify the terminology, just in case it's not clear to everyone. So you kind of have sort of three kinds of switches. So you have your non-PTP aware switch, which basically it just does multicast. It knows nothing. PTP from its point of view is nothing special. Then what was introduced in the PTP v1 standard is something called transparent switch. So in a transparent switch, from a routing point of view, it's basically the same. Everything's going everywhere. But what was added was there's special logic in the switch to update the timestamps to record how long the packet lived in the switch. So the transparent switches allow better time processing. So that's a plus of the transparent switch compared to a non-PTP switch. But from a routing point of view, it's no better than a non-PTP switch. And then what was introduced with V2 is something called boundary clock. And what boundary clock does is it basically it has special logic like a transparent does in the output. But what it does is it doesn't forward the PTP multicast. It actually processes it in the interface itself. So effectively you have basically this little private link. And so that's kind of the difference between the three.
Yeah, and just remember, please put them in the Q&A so we can make sure we hit all those. Question, I know, Mike, I kind of stepped on you. Do you want to add anything before I get into some of the questions and clarification?
So just to mention that when we're doing transparent, we can set up a mirror port on the SE to load all of the traffic. So that's one advantage that a transparent clock particularly has, is it passes everything back, whereas the boundary, you're just looking at a certain segment of the traffic. You're not seeing everything else. So if somebody was hesitant about wanting to make sure that they're seeing everything, then they can use that as a way to capture the traffic in that way. But they have to have a reason to want to really do that.
Yeah, and that's a good point. That's actually Hild's question, which is, so is there an issue with doing like Wireshark or something like that? And indeed that, because what's happening in a transparent switch, not this transparent, but transparent where Lee was talking about, where it's updating the time, you've done PTP enabled on that, you've become boundary clock. What's happening as well is it's taking that packet, punting it to the CPU, it's processed right there on the switch. Versus the mode right here for scalability perspective is to just do multicast. And that way, as Mike was saying, you can take and you can mirror, span, monitor, whatever you want to call it on the switch, is you can take that pristine information and then analyze what's going on. So you can look at the mount, sync, and all the delay request, delay response messages.
So we have lots to cover, so we'll probably have to sort of move on, but we'll sort of come back to sort of the questions there. So a few takeaways is always sort of remember to think about what is the problem you're trying to solve, and then make sure that the solution that you're implementing is actually sort of solving that problem. And you do want to sort of work with your vendors as you're getting into those larger, more complex systems. Second use case here is we want to add PTP to an existing analog reference system. So this was, you would have seen this more as we were adding IP islands to our existing or legacy systems. So this is kind of where we now are bringing the concept of having the unified, where our analog reference and our PTP time must be sort of synchronous to each other. Just looking at sort of what was common you'll see in your analog reference system is you typically have a primary and a backup generator. These would go to some sort of automatic changeover or ACO or ECO, which would then choose which of these two to select. This would then go to a bunch of DAs and cascaded DAs where we would distribute our analog reference here, as well as our other reference signals. And there would have to be some way that these two primary and backup units were synchronized to each other. So either some cross-connected cables or both locked to GPS or something. So looking at some of our sort of solutions or options we have. So option number one is we're going to take a PAL-B with VITC and ST309 date field and send that over to our PTP Grandmaster. Now, as strange as this must seem, this actually applies to both 50 and 59 hertz signals. So with the PAL-B, we get basically a frequency reference for our time. The VITC gives us time, and the 309 gives us date. So with those sort of three components, we can actually get time into our PTP system. And the one important thing to remember is in a PTP system, we're just distributing time. So even though we might have predominantly a 50 hertz or a 59 hertz system, because PTP just works on time, we don't really care about those frame rates as much. Another option, which might sort of be kind of the first option you might think of in a 5994 system, is let's distribute NTSC. And I'll just say that that's a bad idea. The reason that this is a bad idea is with 5994, we don't have an integer number of frames in a second. And so because of that, the time code, it doesn't nicely match up. And so we invented this drop frame time code, which is kind of, you think of it kind of like a leap year. It's got these weird rules to try to keep the time code in line with real time, but it doesn't actually do a perfect job. So every day you drift by 86 milliseconds. And then once a day you do this daily jam where you basically have a discontinuity in your time and you go whack and you reset the time. And from a system which is trying to distribute high precision time, having this discontinuity, which is not well defined, every station does it differently, not every device handles it the same, it makes it very sort of problematic. So really for distributing accurate time, NTSC is not a good choice. So don't recommend that. Another option you could do is use like GPS, or more in general, a global navigation satellite system. So GPS or Galileo, for instance. So you sort of connect the antennas here, and sort of what you're actually then doing is you're not sending time directly between the analog reference and the PTP system. They're each locked to, say, GPS, and because GPS is the same time, you're effectively having them indirectly locked to each other. One sort of downside of that, though, is if, say, say your analog reference, for some reason, its GPS antenna failed, the system would start drifting relative to the PTP time, and that's very bad because then you have two different, your references are different, and so if you have devices that have both black and PTP going to them, it becomes sort of a serious issue. So kind of one thing to watch with that. And then another sort of consideration you may have is, do I connect, in this example here, to the output of the ACO ECO, or do I connect it, one, say the blue network to the primary and the amber network to the backup generator, for instance? One problem you have with that is this changeover unit is making a decision of which of these two SPGs to use as the source of time, and it's using a certain set of logic. And if you've got connections up to the top and bottom, and the PTP is using a different decision, again, you run into an issue that the PTP network and the analog reference may be basically making different decisions. They're not consistent. That can cause you some grief there. So kind of key takeaway is you want to use PAL-B with VITC and 309 for your locking. This is independent if you're a 50 hertz or a 59 hertz area. You do want to use the output from the ACO ECO. And this is also sort of not a preferred method. It's kind of legacy reasons we did this, but we'll see in a moment here the PTP-centric system, and that's actually more of a preferred solution. So talking about that solution, right, this is our next use case. So how do I add an analog reference to a PTP system? So the PTP is the main core system, and now I just have, I may say have certain islands where I want to add an analog reference, or maybe in a greenfield. So we have the question of how do I generate the reference? And as always, we have the question of what happens during failures. Okay, so how do I generate analog reference from PTP? Well, fortunately, we have a standard for that. The SMPTE 2059-1 generation of alignment of interface signals from the PTP epoch does exactly that. It defines how to generate an analog reference signal from time. So what your solution is going to look like, you're going to add to our existing sort of 2022-7 network, we're going to add our two follower SPGs. They're going to take PTP time in, and they're going to generate analog reference out using these equations here. And then we're going to have our changeover unit after. So one nice thing about this solution is, I mean, with the PTP, there's lots of sort of, because the BMCA, if there's failures, the network is going to decide what is the active grandmaster, and your analog reference is going to follow that. So you don't have any of these issues where the analog reference is using different rules and different decision logic than the PTP network. So that's a very important thing to keep all the timing in the system consistent. So that's kind of why this is a preferred solution over the first of generating PTP from analog reference. Looking at sort of a bit of a larger system here. So here we have our IP-centric part of it. And so maybe this section here is some sort of production studio or something where we need, for some legacy reasons, we need to get our analog references. And so in this little section of our facility, we're creating the analog references from our PTP, and then the rest of our system is all sort of PTP based. One of the nice things with the solution here is in the analog reference system, I've got DA cascaded to DA cascaded to DA typically. And if one DA fails, I'll have a large section where I'll actually lose reference, which is very bad. Because in our PTP system here, it's very resilient. If a switch fails or link fails, the network using the BMCA automatically sort of reconfigures and reconverges. And so from a failure point of view, the PTP-centric system is much more resilient, much more reliable than our sort of older analog distribution network.
Hey, Lee, that's a really good point you just made. Go back to that slide, which is in large facilities, if you want to have your analog reference all over the place, right? Or you've got multiple facilities, maybe you've got a break or something like that, or two buildings, then you could use PTP and the connection between them to do your DA, if you will, to DA distribution vis-a-vis PTP, and it's all unified, which is kind of the point of this whole presentation.
Very true there, Robert. Okay. Yeah, so key takeaways here, we've got our SPGs basically tying into our PTP system. We want to have our changeover. And we sort of mentioned that the very powerful thing is that it makes sure that it keeps all the references consistent. Next use case here is I want to get SDI between two locations. I want to get that analog reference to that second location. And I want to do this on the sort of very low cost. So I want to try to avoid having extra GMs. I want to avoid having extra switches just because I'm really SDI to SDI, but I want to do this over some distance. So an option for there is you can have some sort of media node that has some sort of grandmaster built into it. Now this grandmaster, say, isn't designed to replace a fully featured sort of like Tech SPG or a Tech 8000 kind of device, but could be used in sort of this very simple kind of configuration. So I've got a device that can take analog reference in, it can generate a time, and this time is not necessarily a UTC true walled clock time, but it's a time that can be used within the system such that a receiving device could then generate an analog reference out. Then I've got my various SDI ins across my dedicated network to give me my SDI outs. So this kind of configuration by using sort of two dedicated fibers, I have no switches, I have no extra GMs, I'm just using the media nodes which have sort of extra capabilities which can basically act as a small GM, and then can also use the equations to generate an analog reference out. So this covers that kind of SDI to SDI kind of use case over some distance, tens of kilometers or something. Okay, use case number 6 here. So I have multiple locations separated by a WAN. So this may cover something where I have I might have a remote production truck here that I want to connect to my main facility. I may have multiple locations that I'm sharing signals between. And some of the sort of challenges I have is that this network in the middle is maybe not well controlled. It'll definitely have a lot more jitter than I'm used to on my network within my facility. The QoS, I may not have a lot of control over that. A lot of times sending multicast across sort of more, like not like the internet, but sort of more public networks here can be a challenge. And again, we sort of have always our consistent problem of, if I have failures, how do I ensure that everything's converging to the same time? I may also have issues where I have different PTP domains at my different locations. So a variety of challenges we have to overcome. So lots of sort of different options to consider here. So one option is I have GPS at each location. So I have a GPS antenna here at this location here. I have a GPS at this location here. So much like in the sort of one of the previous examples here, I'm using the fact that because GPS has a common time and each of these are locked to GPS, they're effectively locked to each other, although not directly. So one thing to sort of, when it comes to an implementation thing for this solution is, because I don't have PTP coming on my interfaces here, I want to make sure to have some way to block that. So some sort of maybe access control list, ACLs, we'll cover in a moment, sort of this role leader that I can use to sort of block PTP coming from this interface. I may use separate PTP domains to keep them separate. Now, one challenge we have to be cautious of is that, say this GPS antenna fails, then this facility here is going to start drifting relative to this one. So we do have that sort of concern that we need to make sure we've addressed well. Another option is we can try to put PTP across the network. So I may have this to be sort of my in my network, and I want to put PTP across this cloud network to get received here. This has sort of the challenge because of the high jitter in this network and the lack of quality of service. Most devices will have a challenge locking to that PTP because of all those sort of jitter issues, and you won't have very good time here. So really, this is not a recommended or best practice. Another option is you can use time as a service. So what time as a service is, you are getting the time across this network. And you can think of it almost like instead of using GPS, which is getting the time from the sky, is time of service is getting the time across the network. Now, the one difference there is that it's a device that's just been specially designed to handle the higher jitter here. So it's a very purposely built device to handle this very high jitter that you'll see from here. And it may still also put some constraints on quality, and it may have like a separate network. It may be coming from an external network, but it may not be just this sort of the more network cloud that you're using here. So that's another option. And sort of a final option here is we actually don't synchronize. And we just basically, within, say this is a remote production truck, is it has its own time within the truck. So all the audio and video have a relationship, so we can do audio video lip sync and audio video alignment. But to the other facility, we're actually asynchronous to it. And then on our input side, we basically put frame syncs. And so we basically take the signals coming in, we run them through our frame syncs. And this is like very much what we used to do with analog signals. You basically have input frame syncs to your facility to sort of protect and move to that common time base. So as we move to IP, that same solution kind of works with that. The other one to sort of consider there too is, if the distance from this location to this location is large and the time delay is large, then your RTP timestamps and stuff become large, and you actually want to re-timestamp things anyway to kind of move it from the phasing of this network, or from the phasing of this network to the phasing of this network. So in many cases, you'll actually already have to have those frame syncs effectively in this facility anyway for that other reason. So in one way, they come for a bit of free there. Robert and Mike, do you want to sort of add a little bit to this?
Yeah, Mike, you want to talk about the phase alignment stuff? That was one of the questions that just came in fact.
Yeah, so the situation, probably the best part to doing these kind of systems is to actually use the GPS in each location, so that they're timed relative to the GPS signal in each location. That then they are locked together synchronously using those same particular times, rather than trying to get the time through the network, which has some issues if it's not getting all the packets in the right particular time.
And then the other question that came up, is there a limit on the distance in the two locations that they can be apart? And well, there's a couple of things to consider, and Lee touched upon this, which is you don't want to have a shared WAN link, number one, because then you're going to introduce maybe other traffic in there. We want predictable packet pacing, smaller byte packets versus, mixing things with like jumbo and things like that, large MTUs. So that's one. The second thing is, like we were just talking about, phase alignment. And then thirdly is you're better off having a non-quote traditional like MPLS type network. This is more of a dark fiber dedicated link solution. So you have PTP on both ends. And if you have a large delay, then you start to get issues, not necessarily with PTP, but with just the delays that you have to consider when you're transmitting from one side to the other. You just have to tune those values, get the offsets right, so you get the top of frame right. And those are the things to consider when you're tuning your media streams versus PTP. PTP can allot for that with, in a fair amount of time. We're not talking hundreds of milliseconds, but that's what PTP is for, is to know what that distance, that delta is between the transmit and receive on both sides. And hopefully that answered your question. Or Mike or Lee, do you want to add to that, to either one of those things?
Yeah, so maybe just in terms of, is there a distance limit? The answer is no. You've got like the Olympics recently, stuff is coming from Asia to North America. So, these are separated by thousands of kilometers. So, that's quite possible. The one thing you just have to keep in mind is, say when you're doing the Olympics feeds back to North America, because that delay is so large, we have to basically put those frame syncs on the input, so that, as Robert was saying, we want to make sure that the top of frame gets realigned because of just how many milliseconds of just it takes for the speed of light to go across the planet. So as you go for smaller things, if this is a remote truck that's in the next building, then that delay is not as critical, but you do need to sort of keep that synchronization. As that delay gets large, then you sort of need to it doesn't affect the PTP and the time distribution per se, but it does affect the 2110 essence, which is ultimately what we're trying to get to the consumer's eyeballs. So hopefully that adds to that.
And there's one more, and I know we've got a lot going on here, so we'll try to get through some of them. John had a question, and I think somebody just answered it, which is good, which is about frame syncs and analog sync versus PTP on that. That's a good one. And then there's another one from Jonathan. What does SMPTE ST2110 frame sync look like? Do we need a decapsulation STI to frame sync to convert SMPTE ST2110? Does a SMPTE ST2110 frame sync look like? What does it look like?
Yeah, so for instance, the Imagine SMP device is an example of that. So when you do IP processing, whether you go to baseband and SDI out, or you just go IP to IP, it's just a processing device. So the SMP can basically take a 2110 stream in. It does processing, of which one of the many processing features is frame syncing, and then you can either go SDI out or IP out. So
and then last one, which is one that we'll probably have another webinar on, which is cloud. How do you feed PTP to the cloud? There are some services out there that support PTP type of services in the cloud. Amazon is working on one, and there's others like Google Cloud. So that'll probably be in a subsequent webinar where we get, how do you align PTP for those cloud-based services?
Yep. Okay, so we do have a sort of a Q&A at the end, so we will have to sort of come back because we do still have bunch of material to cover. So a few key takeaways here is that there's multiple options. There's sort of various pros and cons depending on what you're trying to achieve. So keep that in mind. But in general, sort of GPS is a kind of a preferred solution. It works very well. It's been tried. It's very easy. So sort of keep that in mind. Then our last kind of use case we want to cover today is I have multiple OB vans at an event. This may be some sort of sporting event where I've got multiple trucks. It's, I don't know, some large event here. Some challenges to sort of considered is you may have multiple companies supplying different trucks. They each have different configurations. One uses PTP domain 42, another one uses domain 110. So you've got different configurations you have to deal with. You may have things where one truck is underground at a stadium, so it doesn't have access to GPS, so that may not be an option. And again, you still have the solution or to consider what happens during a failure and how does your system behave. And then we also have to make sure that we keep our analog reference and our PTP all consistent in all these cases. As we'll see in this example here, we're actually going to build on those previous use cases and sort of pick and choose different components of our previous use case. So this one's actually not a totally unique use case. It's just going to build on sort of using bits and pieces. So one solution here, and this is very similar to the locking PTP to an existing analog reference system. So here we'll have some sort of our central location, or maybe the lead van at this event, and it's going to provide an analog reference, our PAL with VITC and 309, to the various OB trucks. We're not actually going to send PTP between the events. We're going to send this analog reference, and like in that sort of earlier use case, within the truck, then we can then generate our PTP from that. Another option is we use GPS at each truck. So this is very similar to what we were just covering here, the multiple locations separate by WAN case, where we have GPS at each location. Again, we don't actually have PTP going between the devices. We're using the fact that the time is common, and hence they're kind of inferred to be locked to each other. We do have to be careful with the solution. And say if you've got some trucks that are in sort of an undergrounded part of or inside the stadium, they don't have access to the sky, so they don't have access to GPS. Another option is we can basically make this truck as part of our main IP network. So this is really similar to our 2059-7 use case. We're going to provide our blue and amber network cables out to the truck. It's going to then have its PTP domain to be the same as the system that forms one large system. A few things you need to sort of be cautious with this here is, because this truck may be going to various other venues, the PTP domain at every single venue will be different. So this requires reconfiguration of all the devices on the truck to the new PTP domain. So there's sort of configuration challenges. You need to sort of keep that in mind. And you also want to make sure to protect. So from a security point of view, the likelihood of this being sort of a rogue grandmaster or a rogue device is much higher. So you want to make sure to protect the sort of the central lead fan here. So we'll cover a bit more in the security section about this role master, or we'll want to make sure that our P1 values are set, that we can sort of make sure that this doesn't become the grandmaster for the entire system, which we don't want. And then our last solution, which is actually a bit of a new solution here, is we're going to have basically the central facility the same. It's going to be distributing our PTP domain X. What's different about in the truck here is we're going to have a device basically as these come into the truck, and we're going to basically bridge between one domain to another. So it's going to come in and talk to the central timing facility on domain X, but within the truck, it's going to use domain Y. And then this has the advantage that I don't have to reconfigure my truck every time I could move to a new location. So with this here, I mean, for routing the signal, so a boundary clock can only operate, or at least if it's a V2, can only operate with one domain. So here's maybe an example where you might want to use a transparent switch in the van here, because a transparent switch can support multiple domains. So then looking at a sort of picture which sort of ties this all together here. So here's where I have my central location at the sporting event, or maybe this is the lead truck. So to this other van here, I'm control the right monitor here. In this case here, I have to this particular van, I'm going to be distributing my PAL with VITC to these two trucks here. I may have another van where I'm going to do the bridging. So my main facility is running on PTP domain 42. And within this truck here, it's running on domain 110. And I have these bridging devices that are in this particular van. And then this last van in the setup here is sort of unified with my system. So I'm using domain 42 for my main facility, and this truck is configuring to that same domain. And so it's sort of just joining the system here. So you can actually have, like, within sort of a sporting event, not everyone has to be using the same model. So you could have even some trucks using this model, some using this. So lots of different sort of options to choose from there. So kind of some key takeaways there is there's many different options. They're all sort of very viable. Some have some different pros and cons, and it may seem hard, but it's actually not that hard. So, okay, so that's the end of our use cases. Now we sort of want to get into a bit on PTP monitoring. Okay, it's behind. Okay, so PTP monitoring is very important. So we have in our, when you initially set up your system, everything's working well, you've commissioned it, but over time, devices may fail, links may fail, you may network get reconfigured. So you want to make sure that you understand how your device is behaving. So if we look at sort of some of your monitoring nodes, you'll want to be looking at parameters like, is it locked? Which interface is it? Does it have, is PTP present on? What's my grandmaster that I'm locked to? Kind of what's my sort of general time to see if that makes sense. Robert, do you want to sort of comment what kind of monitoring you can do on the switches?
Yeah, there's a bunch of it. Now we'll just be really quick because we're going to run out of time. Is the switch has ability, like we have show PTP monitor. You can see the offset from master on it. You can see the statistics coming from a device as well. So if somebody says, I'm sending you PTP, you can look on the interface and see if they're actually sending the PTP messages and we're responding to it, see if it's configured properly. And we have something called Cloud Vision Portal. We call it CVP. We can look at the statistics. We can also see where the master and slaves are. We can do all kinds of things. I mean, as they say, you're only as good as your tools. Speaking only as good as your tools, the great product that's out there that is kind of the platinum standard of tool testing for both PTP and Essence Streams is the Prism.
So here I'm just going to start a little video to show you. On the left-hand side, I have the IP session. So this gives me my Grandmaster ID, and it will show that. And here in this particular case, we're going to put in the IP status. We're going to look for our PTP domain. And we can see that PTP domain was 110 for the messages, but we're actually set up here at 127. So we're going to change that value. And we're going to bring it into 110. And now what we can do is look in the IP session to see how quickly we can actually lock to that time. So we've got our Grandmaster ID that immediately popped up on our phase lag value, which is the reverse and forward path average that's shown as a graphical display in the lower right-hand side. So here we can see that. I'm going to switch from the day view, which shows you what happened over the last day, to what you can see in the last 5 minutes, which is when that change occurred. So we had a period of time where we were not locked. We were on domain 127, and then we pulled in to lock to our 110 domain. And in the upper display, I'm going to show you, again, a 5-minute window, this time of the forward path between the leader and follower. And so in this particular case, this is the region here that was sort of not locked for a period of time where it's flatlined, and then it pulled in the range for the PTP to lock to that domain of 110. And so you can see the forward path and the particular graph on the two path signals, and they should both converge over the course of the network lock to produce the same or similar offsets between these two values. And that's what they did as they locked from domain 127 to 110. Back to Lee.
Thanks, Mike. So one issue that sort of comes up with PTP device monitoring is that different vendors are doing things differently. So one vendor's got I have a parameter called locked, another vendor has a parameter called not locked, and a third vendor has no locking status at all. And this makes it very hard on your monitoring system to consistently be able to report some of these critical parameters. So to help address that, SMPTE has created a drafting group here working on something, a recommended practice, RP 2059-15. And what it's trying to come up with is some common statuses that are like every device should have. So something like locked, I mean, that's just every device should have that. And we want to come up with a common encoding. So do you report locked or not locked? So you want to come up with this common language. And then the way we're sort of representing that is using something called the Yang data model. So using this Yang data model, we're coming up with sort of parameters that, and it's an RP, so it's a should, but it's basically trying to provide some consistency in the industry. Now, within SMPTE, typically we have an engineering group that has lots of experts, and we sort of come up with what we think is the best standard. Now, something SMPTE's been doing a lot of newer things is something called the Public Committee Draft or PCD process. And what we're doing with that is once we come up with a draft, instead of sort of publishing and then sort of waiting a year for the 1-year review, is we want to get feedback from the industry, from other implementers and users to say, hey, does this standard make sense? And so that's what we're using this new process on the 2059-15 monitoring RP. And so that the first draft is available here on the SMPTE GitHub site, which I put the link there. So what we've done is we put this out, we've got feedback from the industry, we've now created a second version, and we're actually just about to put the second version out for a final set of comments before then we actually then publish this RP. So a couple notes there is, if you're interested in contributing, I encourage you to please look at the RP there, provide some feedback, note that there's a version 2 coming, and don't put it sort of in your sort of project definitions yet, but just note that in the near future, you'll want to start asking device manufacturers to support this, but it's not out yet. Okay, into our last topic here, security. So with PTP security or 2059 security, we want to do sort of threat modeling. This is not sort of specific to PTP that you want to do this with any sort of security analysis. So threat modeling is the process of identifying, enumerating, and prioritizing the various threats. Now, fortunately to help you, SMPTE has a study group, the PTP Security Study Group, which has published one report and is working on a second report. That first report sort of goes through some of the threat modeling for you and identifies a bunch of stuff. So if you're doing your threat modeling, that SMPTE study report, which is available on the SMPTE website for free, is a good starting point. When you're considering sort of your threat modeling, what are the different attacks you may have on a PTP system? So one thing is you might want to change the time. So change the time a year from now, and then things like your licenses might expire, your playlist will be all wrong. Another thing you might be trying to do is disrupt the time. So in a 2110 system, the RTP timestamps are created from the PTP time. And so if you disrupt the time, you disrupt the RTP timestamps, and that causes receivers issues receiving the signal. Another thing too, when you're changing the time, in addition to say jumping the time forward a year, what you can also do is change the frequency. So if you change the frequency, say by 1,000 ppm, if you looked at the time on a wall clock, it'll look to be more or less right, but it'll be sort of drifting. And then many devices say like 1,000 ppm, they can't lock to it. So devices will sort of lock and unlock, and in your alarm monitoring system, you would see all these devices going to lock and unlock state. So something as simple as changing the frequency a lot can also be very devastating to your system. And then the last kind of attack that you may be doing is trying to stop the time distribution completely. So kind of a denial service. So devices will go into free run, and then you'll have sort of asynchronous performance. But not every device supports kind of an asynchronous thing. So for securing, you want to secure all the critical parts. So your grandmasters, your switches, your media nodes. We sort of covered your monitoring system, so it's very important. The monitoring system allows you to detect changes in your system, which can indicate that an attack is going on. So having that monitoring system is very critical. One thing to pay sort of close attention to is the TLV management messages. We'll cover in a second here the sort of boundary clock feature, but the TLV management messages go through boundary clocks. And so you can still do a denial of service attack. The new version of the 1588, the version 2.1, does add some security features. So take a look at those. Looking at sort of each device in a bit more detail. So your grandmasters, and this also true to all the devices, you want to make sure that your management interfaces are properly protected with passwords and secure shells and stuff. Because if you get access to the management, then you can change any parameter, and obviously changing that on the grandmaster sort of will have a bad impact on your PTP system. You also want to sort of protect your GPS antenna. A couple different ways that people can attack those. They can do a jamming technology where you try to overpower the signal. The GPS power level is very low. So jammers these days are very readable. For like $50, you can buy one. If you try to point that at an antenna, you can try to block that. There's also technology you can get. So basically satellites are above us. So we know that GPS satellites should be above us. And so if the antenna sees power below the horizon, it can put in technology to basically prevent below the horizon power from interfering with the antenna. Another kind of attack is a spoofing attack, where you basically try to become a fake satellite. So you kind of overpower the signal, but instead of just blindly jamming it, you actually send proper information so the receiver thinks you're a satellite. And then from that, you could say skew the frequency or do something like that. And then sort of anti-spoofing technology that can be bought. Another thing to sort of consider is sort of some timing diversity. So you may want to use multiple GNS constellations. So you might want to use, say, GPS as well as Galileo. So you've got multiple services. Or you want to use sort of service diversity. So you're using something like GPS, which is coming from the sky, and then using something like, say, NTP to sort of validate your time. So like NTP does not provide time which is good enough to lock your station to, but it does give you sort of a point of reference so that if some person was trying to change the time in the station, you could compare to see, does the time make sense? So it gives you sort of something to compare it against. If we look at the switches and the media nodes, so the sort of most powerful thing you can do for securing a PTP system is to use a boundary clock switch, and then you want to use this leader only feature. So it's not in the standard, but basically every switch supports this. So in our systems, in our 2110 systems, this is an engineered network. So we know that, interfaces up here are connected to legitimate grandmasters. And we know all these interfaces here are connected to our media nodes. We should never, ever see a grandmaster there. And so if I turn on this leader only mode feature, then if I do plug in sort of a rogue grandmaster, and this could either be either intentional or an accidental thing, is the switch will basically ignore any grandmasters here. So this is a very, very powerful thing. Basically, rogue grandmasters are non-issue then. Another little feature you can turn on, the 2110 standard requires that you support this follower only mode. So I can set this device to say, I will never try to become a grandmaster. And that doesn't sort of help you because, obviously if I'm plugging in a rogue grandmaster, I'm not going to turn that on, but it can sort of help your monitoring system with sort of false positives. And the one good thing, I've spoken to many, many security experts. I've attended lots of PTP conferences. It's used in many different industries. And unfortunately, there's never been a documented attack on PTP. There's been attacks on the GNS. That's happened many times. But fortunately, and this could always change, that to date, there's been no attacks on the PTP infrastructure itself. So that's a good thing. And then definitely by using our boundary clock switches, we can sort of open up our networks pretty good. So in conclusion here, so there are different use cases requiring different topologies. We sort of want to keep in mind what is our sort of design goal on each of them, what are we trying to achieve. We want to use that PTP time sector distribution with those local analog reference islands. Monitoring is very important. We've got the new 2059 coming, so 2059-15 coming. For PTP security, we want to make sure we design this in, it's not an after the fact. We want to use those boundary clocks and basically for all our switches. We want to use that rule leader feature. We want to have our monitoring to check for changes, look at things like grandmasters. Is it the correct grandmaster for our system? We want to follow all those best practices from our previous presentation. And if I design, implement, and commission my system correctly, then PTP is easy and it works really well. Just a reminder that next week we have our third in this second webinar series. We have the Journey to HDR, UHD, and 4K and beyond. And with that, we'll kind of open up to questions. We've been answering questions as we've been going, but I guess we'll sort of go a few minutes over here and answer a few more questions.
I think all the questions were answered. John did post the fact that there's another presentation coming up with the Society of Broadcast Engineers, SBE.org. Check that out. We got John Myatt presenting at that one. And then Mr. Waitson, was there anything that we didn't cover? I think Lee covered pretty much everything that we had prepared for.
Yep, I think so. There was one question in here. I noticed that I just reiterate again. So somebody asked, what if we don't have a GPS lock in our system and we want to synchronize our SPGs together? So there are a couple of ways you could do that. You can decide to make your primary unit the master and provide its PAL VITSI output to the second backup system. So that way then they're synchronous. It's kind of a free run mode for if you don't have GPS available in your system. The recommendation again is to lock the primary PAL output to the backup, and then they'll both be synchronous in time information using VITSI and the SMPTE 309. So that was one question that got asked now.
I think we're going to have to come up with some more acronyms to string along in a single sentence. So with that, is there any more questions? Last chance for questions with the panelists here and all the people that are presenting. If not, Gina, would you like to close us out?
I see. Looks like we have. Oh, no, I take it back. Those were been answered. So.
Yeah, we've had a great number of questions come in through the back, and our team from Imagine, Arista, and Telestream have all been working super diligently to get to those answers. We really appreciate your time, and thank you everybody for making this an interactive session. Lee, thank you for the rundown of everything. Robert and Michael, of course, for your input and banter as well. We really appreciate it. Lots of great information. So yes, this will be recorded. I'm sure many people are going to want to go back and catch a few things they may have missed. So session 1 and session 2 and session 3 will be recorded. Session 3, of course, coming up next week, same time, same place. We hope that you'll be able to join us then. Thank you very much, everyone, for your time. Thank you to our partners, Arista, Imagine, and Telestream. We appreciate everybody being here. We hope you have a great day. Take care.